Okay. In our last lecture, we tried to solve beam problems by using stiffness matrix, direct stiffness method. We are having a concentrated load P at one side and then one fixed at one side, and then there's a pin. There's a pin, or there's a yeah, you can say it's a pin at point number 2, a roller. Then we calculate the stiffness matrix, and then we try to find the displacement at all the location. So when you solve beam, remember that we always start with the standard stiffness matrix. So in your coming test or exam, you write the stiffness matrix, and then you will get 1 mark for the standard stiffness matrix. Remember to write the correct one, yeah. And then you put all your point in the global matrix, yeah. So this is for single element, and then this one is a combination when you combine all the all the 2 element into here. Okay, so just to explain that these 2 column is 0.1, these 2 column is 0.2, these 2 column is 0.3. Yeah. Okay. Okay, so each point have a displacement. So you put for element 1, you see that is having 0.1 and 2. So this 4 matrix here represent the element 1. This element 2 is having 0.2 and 0.3. So you are having this is 0.1, 0.2, 0.3. So you are having, for element 2, you're having 0.2 and 0.3. So you are having this column. Okay, then you combine, you get a big global matrix. So at this stage, you should already know how to combine all the metrics together. If not, you need to go back to the previous example and practice on it. Okay. We have gone through, and then we put the stiffness matrix into the F equal to KD force matrix, where we'll put force and moment in one side, and then your displacement at one side, K in the middle. Yeah. All right. So again, I'm rewriting. You see the one on the left here, the stiffness matrix, the global stiffness matrix here. The bottom here, I write symmetry, is because the number at this mirror axis is actually the same. So you see here is -12 and so on, yeah. So this is to save my time when I'm preparing the slides. So in your test or exam or assignment, you try to avoid using this word, yeah. You need to write the full matrix in your answer. Okay, I just did a comparison so that you know what is meant by symmetry when we in our lecture, yeah. Okay, so last lecture we already stopped at this point, and then we apply the boundary condition. So point 2 not able to move, because when you press down, point 2 not able to move down, yeah. So V2 equal to 0. V3 of course is inside the wall. There's no displacement in vertical, and also there's no rotation can be done on point number 3. So V3 rotation 3 equals 0. You put into this equation, and you can close those relevant row and column in the matrix. So V2, you just close the V2 row and column. So 1, 2, 3, this is the later one. You close all the later row and column. And then the rest, you just copy one more time to a new space in your answer. And then you compare with the system. So F1y is P, and remember to write negative if it's opposite the y-axis. Yeah. So we have P here. And then M1 here, we don't have moment. We don't have moment, so 0. And then M2 here, there's no, because it's a roller here, roller is free to roll. So we don't have moment at point number 2. So 0. Then the rest is just you solve like what you did in your homework. Yeah, you did a reverse matrix, okay, and then you solve it. Okay. So basically, you just what you did is that, let's say this is your A matrix, EI divided by L3, and this is your displacement. So what you did to solve your displacement will be you are moving your, okay, I'll write something somewhere. Okay, let me clear the slides so that I have space. Okay, just now you have your force, your K, and your displacement. So you are solving displacement. So what you did is that you put your K to another side. It's just that F and then times the K inverse equal to displacement. So when you move your K later on, remember you can always move the constant value of EI over L3 to the left hand side. All right. And then you try to solve the question. So you try to solve for the inverse matrix, then you put into the equation, and then you will get the answer. Yeah? If you're not able to do inverse matrix, you can go to a slower way when it comes to your test, when it comes to exam or assignment. You can use a simultaneous equation. Yeah, substitute here and there, and then you will get the answer. Okay, so after we solve these 3 equations here, right, you'll get your displacement number in terms of P, L, 3 and 12 EI. So this one is in P because P is a constant value. There will be a finite value for P. There will be a finite value for, there will be a value for your length. There will be a value for your modulus Young or elasticity constant and your second moment of area. This PLEI is a constant value. So you can, that's why you can do it in this way. Then maybe in your coming test or exam, after you done solving in terms of PLEI, then the next section, I will give you a number for P, I'll give you a number for L, I'll give you a number of E and I, then you solve it in maybe a section B or section C. All right. So after you solve, you get a negative number. It means that the displacement is going down. There will be a meaning. So in your coming test or assignment, when you get a certain number in positive sign or negative sign, you need to know how to explain it. Yeah. So in this case, when you solve this question or tutorial question, your V1 is negative something. So it means that the displacement is going down. Where it's logical, when you look at the picture, the P is pointing down and the displacement should be going down. Yeah. Then the slope or the rotation will be positive. It means it's an anti-clockwise direction, right? Rotation number 2 also positive, means anti-clockwise. Now today it will be, then after that you done it, you put it into the F equal to KD equation again, you replace it, and then you try to solve for the remaining on the left, yeah, remaining your force component. All right. Then after that, you'll get your force equal to 1P, your moment 1, 0, and so on. You'll get all the other missing component just now. Yeah. All right. Remember that just now what we did is that the blue line here, what we did is that we just close it temporary. We do not cancel it there. We just close the respective row and column to help us to focus on the on the one that we already have the number to help us to solve. Yeah. Okay. So we already get the F and your D, your F component and your D component. Today, our focus will be on the your free body diagram. Yeah, what we did just now is on the global scale where you have all the capital F and M. This is on the global scale. So when you come to your final exam, it will be a little bit deeper. We will go to element. Yeah, we will look at element. So how do we do analysis on element? So for element one, you only see point 1 and 2. Yeah, for element 1, you only see point 1 and 2. So you rewrite the matrix form F equal to KD. In this case, your F component all is small alphabet. F1y, M1, F2y, and M2. And the stiffness matrix will be the same. The K will still the same. Only be careful on the displacement here, because element 1, you have displacement 0.1 and rotation 0.1, and your displacement 0.2 and your rotation 0.2. Yeah. So be careful when you rewrite the global matrix into element matrix. Yeah. And then you put in the displacement that you found just now, the V1, the rotation and number 2. And then from here, you have 4 equations. Yeah. V2 is 0 because we know that in this point, under the pressure, under the force at point 1, the point number 2 not able to move. So V2 equal to 0. You have 4 equations. You have 4 unknown here. You're able to solve either using simultaneous equation, or you can use inverse matrix. Yeah. So from here, you're solving, you'll get the 4 unknown over here. Yeah. F1y equal to negative P, M1 0, P and minus PL. So as you can see here, when it comes to tests, you need to know how to explain all the positive and negative sign. So for example, in this case, F1y equal to negative P, you need to say that, or you need to write something for saying that F1y will be going down. There's no moment at element 1, at point 1. And then for F2y at point number 2, there will be a positive force going up. And then for moment number 2, it will be a negative PL. It just means that the rotation at point number 2 will be clockwise direction. So after you get the value on the left hand side, you're required to draw a diagram for each element. Yeah. So what you see on the screen here is what you already solved for element 1. You have all the displacement, force, and the moment. Then you put all this number into a free body diagram. So how you draw free body diagram is based on your answer. So you draw the element 1, you draw this line, and then you label as 1, element 1, and then you can pinpoint this one as 1 and 2. The rest, you just follow your answer. At point number 1 here, your answer is minus P is going down, so you draw P going down. There's no moment, so there's no moment sign over here. And then for point number 2 here, you have F2y equal to positive P, positive going up. And then you have a moment negative PL, which means you have a clockwise direction of moment. Then this one is your free body diagram for element 1. Okay, so look for the keyword in the question. So if that particular section asks you to, after you solve for the force and moment, you'll be told to draw a free body diagram to show that you understand what you are calculating. Yeah. So you need to know to draw the diagram, the second diagram on the screen here. You need to know how to transfer your analytic answer into a diagram. Any question for the diagram? Any one of you want to ask me question? You don't understand how to transfer the numbers or the answer for force and moment. Like you understand, eh? Okay. Singi, you okay?
Yes.
Okay. Katana, you all right?
Yes, sir.
Okay, good. All right. Now you do the same for element 2. You calculate for element 2. You will get the second free body diagram, something like that. Yeah. So remember, yeah, need to know how to draw the free body diagram. I think this one you learn in your static already from the calculation. Okay. Then you also need to, the slide that you see on the screen right now is the capital F and capital M. So after you solve for the global, you also need to transfer all the answer into a diagram, right? So this is the force and moment diagram at a global scale. So you see that this is a capital F11 equal to a negative P. So you just draw is going down the P, and then there's no moment at point 1. F2 also same, positive going up. There's no moment at point 2, and then there's a negative sign of force in point number 3 going down, and positive is mean anti-clockwise. Yeah. So the previous lecture we stopped at finding the force component and the displacement component, and then today just add on a little bit on a free body diagram, how you transfer all the answer into a diagram form. First is the free body diagram for the element, right? On this screen here, this is for element. And then another one is the global answer for the force and moment on a beam, really this one. So basically, if you have two element, you have two element diagram, really this one, and then one global diagram for the force and moment, really this one. Okay. So normally, how much it costs in the exam? It will cost 4 to 5 marks for each diagram. So for example, if you're having this kind of question in exam, it will cost you about 12 to 15 marks just to draw the diagram. So imagine if you did wrong or you did it some error in your calculation, it will affect your free body diagram. Yeah, you're going to snowball. So be careful when you did calculation in your exam later on. Yeah. Okay. And then after that, from the nodal force moment diagram, this one is the global scale. So you see that we transfer the diagram that you see on the screen on the top left here. We already transferred to the diagram, the second diagram you see on the screen here with the P and the moment at each point. And after that, you have to recall what you learned in your static or dynamic class. You need to convert the beam diagram into a shear force diagram. So shear force diagram is something like this. Yeah, the shear force diagram, it means the shear force versus the length of the object. Yeah. So you have a P, negative P going down. So your shear loading will be going down. And then it will continue until point number 2. You have a 5 over 2P here. So it will go up. This magnitude will be 5 over 2P. So you already have a negative P here, which means that you will have 2 over 2P at this portion. So you have a remaining of 3 over 2p going up here. So you draw until 3 over 2p, and then you draw a straight line and then close the loop. This is a shear force diagram for beam. Yeah. So I'm not going to explain how you get shear force diagram. So this one you already learned in your static and dynamic module. This is also part of your final exam. Yeah. So you need to know how to draw the free body diagram for element 1 and 2. For example, in this case, 1 and 2. And then you combine, become a nodal force and moment of the beam. You get the third diagram, that what you see on the screen here. And then you need to transfer it into a shear force diagram. You need to give a shear force diagram, something like this. Yeah. So I will left you to go and back and do your own homework for the shear force diagram. Yeah. Then after you did the shear force diagram, there's another diagram that you need to show us when it comes to your final exam. It will be a bending moment diagram. So bending moment diagram is M versus L. Yeah, M versus L. So there's no moment at pin 1, and then when you move across the beam, you will come to negative PL, and then you will go up to to the remaining moment value. So in this case, at point 3, you arrive at PL divided by 2. Again, bending moment you already learned in your static and dynamic module, so I won't go deep to explain. We assume you already know how to do this one. Right? So just to let you see the whole picture when it comes to your final exam, what we expect you to understand is that you need to know how to build normally when it comes to final exam, the first section, maybe section A, is to build the stiffness matrix. Yeah, so this is the first we expect from you. You need to know from how to build the element 1, 2 into a global matrix. Of course, in final exam, it will be 3 elements. Yeah, it will be 3 elements. 2 elements will be not at the final exam standard. So you go to maybe 3. Yeah. So I will let you give you more detail when come to final exam. Yeah. So at the moment, what is important is that in this section, you have to know how to convert the individual matrix, K matrix, into a global one. After that, you write F equal to KD, solve for the global force and displacement. Yeah. So after you build the matrix here, you solve for the displacement, the D component on the right hand side. After you solve it, how you solve it? You solve it based on the boundary condition. You look at the picture, which point cannot move, which point can move. Then you close the respective row and column. You solve for maybe 3 unknown. Then after that, you replace back the displacement number. You solve for the left-hand side, the force component. After you solve it, then what we expect from you will be the diagram. You expect to know how to draw the free body diagram for each element. Yeah, this one, right? You expect you to know how to calculate the individual element, F equal to KD again, right? Remember the small f, small m. After you get all these number for the F element, for the F component, you draw it on the free body diagram. What you see on the screen here for each element. Then after that, expect something will ask you to combine all the force and moment in the global scale. So this one you look at capital F and capital M. You look at your answer and then you transfer the mathematics form into a diagram form. All right, one is for element, one is for the global scale for force and moment, on the pin itself. All right, or another keyword is nodal force moment. It means that it asks you to draw a diagram at a global scale. Right, means you transfer the question diagram into a force and moment diagram. Then after that, I expect you to draw a shear force diagram and also a bending moment diagram. Okay, any questions so far before we move to the second example for today's lecture? Any question?
No question.
Yeah. You guys want to have a break, or you can go ahead with the next question? What do you think? You guys want to have a short break, or you can continue and then we end the lecture?
We continue.
Continue. La, you okay? Continue. Singy, okay?
Okay.
Yes.
Okay, we continue. Okay, so this question, it will be three, also two element, but there's a lot of point there. Yeah, there's a lot of point there. So if you look at this diagram, it's a beam diagram. So it will be the same as your tutorial question or your handout question. Yeah. So if you look at the diagram, you have point 1, point 2, point 3, point 4, and point 5. So each point have some forces there. So on point 1, it built in a wall. Point 2, there is a focus load. Point number 2. Point 3, there will be a roller pin. And then there will be a focus point again on point number 4, and then point number 5 built in the wall. So there will be a bending behavior under these two load. The dashed line will be the end result after the loading. It will be a bending. Point number 2 and point number 3. Yeah. And the length is given in this case. In previous example, you just given the alphabet L. In this case, you're given a finite number of length, 10 meter, and also the force also given a finite number, which is 10,000 Newton. Okay. All right. Now the question will go like this. Will ask you to determine the nodal displacement and rotation. Now nodal displacement, it means that you need to find the displacement at each point. Rotation at each point. So you will have each point you have one displacement, one rotation. So you have 10 unknown there. Okay, 10 unknown is a very big question. It's a very big matrix later on. Yeah. So and then you need to find the global nodal force. Nodal global force means you transfer this diagram into force diagram. Yeah. So you later need to find the capital F and the capital K later on. And then you analyze based on the number, the point number 1, 2, 3, 4, 5. As we can see in the diagram, the beam is fixed at point 1 and 5 and has a roller support at point number 3. Vertical loads is given, and E and I is given in this case. So this example is about solving matrix with finite number. Okay, how we solve it? We just repeat the principle like what we learned this morning. Yeah. So for element 1, you write the stiffness matrix for element 1. So in this case, you break this element into a few elements. So element 1 with point 1 and 2, element 2 with 2 and 3, element 3 with 3 and 4, element 4 with point 4 and 5. Okay, stop me if anything you don't understand. Stop me. Don't let the question get up. So stop. Clear your doubt before you move forward. So as I make some notation on the screen here, you will see that I add a black color notation. So for element 1, you are actually looking at vertical displacement at point 1 and rotation point 1, vertical displacement point 2, rotation point 2. All right. On this side also same. You can write with your pencil. In exam, the black mark notation you write with pencil is just to let you guys to know how to put all this number into a global matrix later on, because you have 4 elements. So element 2 also the same number. However, the number represent different point. I add in the black color notation for clearer understanding. So if you look at element 2, the point is 2 and 3. So the first column will represent vertical displacement 2. Second column will represent rotation 2, and then third and fourth will also followed by the point that on the element 2. So you have 3. So at this moment, you should already know how to write, how to identify what all this number inside the matrix already. Yeah. So element 3 also the same. Only element 3 represent by point 3 and 4. So I also put in the black color notation for you, just to show that later on you will arrive at very big stiffness matrix. So you have vertical displacement V3 and rotation 3, and then 4 for the remaining third column and fourth column. And then you repeat the same for element 4. So element 4 you are seeing 0.4 and 5. Although the number will be same, but add in the notation for you. So V4 means that vertical displacement 0.4, rotation 0.4, and so on, 4.5. Okay. Any questions so far for the element stiffness matrix? Anything that you're not sure for the black color notation that are right on the screen here? Any question?
No question.
Okay, good. Then the next step is just to put in one global matrix. Now again, go home and do homework. Yeah. If you don't practice, you'll be panicked in exam. Yeah. Yeah. So that's just a reminder. Huh? Just a reminder. You need to know how to put all this into a matrix based on the notation here, right? So if you write in the matrix later on with this capital K, expect something that very big matrix. Yeah. So you have element 1, 2, 0.1, 2, 3, 4, 0.1, 2, 3, 4 here. So each one have 2 columns. So you have 8 rows of number. Each point will have two degree of freedom. You have 1 row for V, 1 row for rotation. So you have 8. 1, 2, 3, 4, 5, 6, 7, 8. So same with this one. Stop me if you're not able to understand why we're having a 8 row and 8 column when we come to global matrix. Stop me if you're not able to ask me question now. Yeah.
So
Yes.
I think it's 10.
Oh, sorry, 10. Yeah, correct. So we have 5 points. Excellent. Yeah. Okay, good. Yeah, should we have a 10 row and 10 column. Correct. Yeah. So it means that Singy, you understand. Okay, good. Okay, we move to the next slide. So I'm showing the total global matrix on the screen here. Again, do your own homework. Try to learn how to put the individual matrix into a global matrix like what you see on the screen here. It's a very big matrix. It looks complex, but actually is not that complex. Yeah, it's just plug and play. You just put the number into the correct parking lot. Yeah. Okay. So again, go home and practice on this example. All right. So we're going to move on with all this, and then after you build the global matrix with the global stiffness matrix, and you put into F equal to KD form. It looks very complex, but still back to the basic. We still need to write F equal to KD. So F on the left hand side, you see that when it comes to a beam analysis, we only seeing force and moment, K and D. Yeah. So again, when you did your test one, don't confuse with trust, or don't confuse with this chapter. All right. It will be a different number on the left hand side and right hand side. Okay. So I'll just show you how I build. So all these are just a side note. Okay, so for element 1, I just highlight where it is all this number. Then element 2, where is all this number. Element 3, where is all this number. Element 4 and element 5, so on. Yeah. Okay. As for element 4, we have 4 elements, correct. Okay, so I've highlight with all this notation. It will help you in your revision. So at least you know how or why there is a plus number there inside there. Yeah. Yeah, this if you have there's a space in my slide here, it means that there's a zero point there. Yeah. Then after you get F equal to KD, you apply the boundary condition. You look at the system. Whenever it cannot move, you put 0. Then you can close the particular row and column. Then you look at the remaining number, you pull them out, you put one side, and then you solve for that particular matrix. So in this point, we apply the boundary condition. So if you look at point 1, we know that when you build inside a wall, it is this point here. You build inside a wall, you don't have vertical displacement in this point, but there's a moment there. Yeah? No, there is no rotation. Sorry, there's no rotation at point 1. Rotation. So point 1, V1 0, rotation 0. So you can start and close the respective row and column in the global matrix up there. So I did it with the red line, that's what you see on the screen. I close these two, and then I close the 2 column on the screen. Yeah. This is we are start applying the boundary condition already. Then we go for the third point. Third point is a roller pin here. So when you have a roller pin, you have a rotation. There's a rotation angle there. So we only cannot move vertically. So V3 equal to 0, you start to close the V3 column, and then row also. And then you look at number 5. Number 5 also, it built inside wall, it will be the same scenario with point 1. So V0, rotation 0. Yeah. So you start to close all these things. So you have, when you apply the found boundary condition, you reduce your matrix, 10 times 10 matrix, you reduce it to 5 times 5. So you have all these 5 number represent F2Y, M2, M3, F4Y, M4. Yeah, you have only 3 unknown here, 5 unknown on the left, 5 unknown on the right hand side, and then you have a 5 times 5 matrix. All right. So when you close, remember that you have EI divided by L3 outside there. Yeah. I think I have a typo error in my formula here. It's a EI, not L. Yeah. It's a EI L3. Right. So you arrive at what you see on the screen at the bottom of the screen here. So you have 5 times 5 matrix. The rest is just to solve 5 simultaneous equations. You have 5 equations there. You're able to solve the equation. In this case, you're able to solve it very directly because the force number is given, the displacement, the length is given. So The L here, you can just substitute and calculate it later on. Yeah, E is given, I is given, L is given, so you're able to arrive, solve it more quickly with all these number. Yeah. Yeah, of course, I will recommend you do it slowly, like what I did on the screen here. So you apply boundary condition back to the screen here. So when you simplify the global matrices now, you are simplifying a global scale F equal to KD. Yeah? So you have having a capital F, capital M here. So you look at the system, the outside system that you have. So what you know from the diagram here, you know that you have, for point number 2 here, you have a negative sign of 10,000 Newton. So you get negative 10,000 for F2Y, and then negative 10,000 for point number 4, which is F4Y. And then for this moment, we know that inside wall, there's no moment. And for point number 3 here, M3 here, once you have a roller, and roller here is free to move, so there's no moment. And point number 5 also 0. So we have all the number here, 5 equation on the screen. You're able to solve for all these unknown on the right hand side here. Right? The remaining slides is just mathematics steps. So I will treat it as your homework. So you go ahead and solve it. Yeah, you need to go and really get your hands-on experience. Yeah, you need to go and calculate it. All right. So there's some notes there why there is a 0 sign there. So if you look at the diagram here, we know that our rotation at point 2 will be 0, point 3 will be 0, rotation point 4 will be 0. Yeah. So this is a boundary condition when we apply to solve this one. So with this boundary condition, we can further reduce the equation into we have five unknown here. After we applying the boundary condition again for the slope or rotation, 5 we know 3 reduced to 2 equation only. Yeah, we close it. So you only arrive at a very simple 2 equation simultaneous equation. From here, you have a EIL cube, and then you have all the numbers inside the matrix. You have 2 equations here. You can solve for V2 and V4. So you get the number for V2, you get a number for V4. Yeah. So I'm not going to do the mathematics for you. It's just that I'll show you the principle. So there's a number for vertical 2, vertical displacement 2, vertical displacement at point 4. Once you find the answer, you recycle back the answer back to the equation, and then you solve it. Yeah. So you substitute back to the global scale matrix, like what you see on the screen here. Then you can find all the numbers there. Okay. After you solve for the global scale, the force on the left hand side, you solve for individual element where you change the capital F and capital M into a small one, where you cut all the element into small pieces. You look at individual element. So there will be 4 more diagram later on. You will see element 1 with point 1 and 2, element 2 with point 2 and 3, element 3 with 3 and 4, element 4 with 4 and 5. Okay, so I'll show you the first one for element 1. So you put F equal to KD for element small f, small m on the left hand side. From this the format or structure of this mathematical model, you know that you are going to solve for element 1, which is come with the point 1 and point 2. You know that you already found what is vertical displacement, and the rotation, all these are 0. So from here you can find the unknown on the left hand side here. Yeah. then this is just an extra notes. So you solve the question on one side. So if you look from point 1, 2, 3, you can see it as a roller point here as a fixed support. You can, when you dismantle the diagram from point 2, from point 1 to point 2 to point 3 up to this point, you can represent this portion as the diagram, what you see on the screen here. Okay. All right, and then I will not go to the bending moment, the shear loading, the shear diagram, and all this. Yeah, from there, we will transfer what we learned this morning into this example. Yeah, in this example, I don't show you how to draw I don't show you how to draw the shear diagram and also the bending moment diagram. So you need to know how to transfer into individual free body diagram with the force and bending moment, and then you transfer it into a nodal force, into a shear diagram and bending moment diagram for beam. Yeah. So this example that we see just now is a more complex case with 10 times 10 matrix, very big matrix. However, the way we solve it still back to the fundamental idea. You solve it one by one and then apply boundary condition, you're able to find the answer. Okay, I think we stop at this example. We will continue with another 2 example in our next lecture. Okay, let me stop the recording.